So before looking at the details of the reactions of benzene, I thought it would be helpful to go back and review aromaticity and what it means for a molecule to be aromatic, how you determine whether or not it's aromatic, and then go over the basic mechanisms for electrophilic aromatic substitution reactions, and sort of discuss a little bit about why we do substitution instead of addition. So before we get into talking about aromaticity, we have to review a topic called resonance energy. Resonance energy is the stability gained by having delocalization. So let me write here, stability gained by having delocalization. Okay, so to see this, really what you need to do is you need to look at molecules that perhaps look like this versus looking like this. And then what we do is we do the hydrogenation of these compounds to form their alkanes. And you'll know that both of these form the same alkane. So this is a H2 with a palladium metal catalyst of some sorts. Okay, so when we do that, what we find is that the change in energy for the two compounds, let's call this A and this B, the change in energy can be graphed, and we have molecule A here, and then we have, this is C, that's down here. They have a common product, that's C. What we would find for B is that B's energy is here, somewhat below, by a few kcals per mole, and I'll show you that in the next slide, that B is lower than in energy than A. And we get that because this energy is smaller. The energy to go from A to C is greater than the energy required to go from B to C. All right, so and remember this is the reaction coordinate down here. Okay, so to put some numbers to this, when we do the hydrogenation of cyclohexene with hydrogen and a catalyst, we get about 28.6 kcals per mole. Now, if we extend that idea to benzene, right, oh, and by the way, for the difference in energy of molecules A and B from the previous slide, we find that B is lower than A by about 4 kcals, 3.7 kcals per mole of molecule. And the difference between these two has to do with the conjugation of these two bonds. That is, this molecule is conjugated because it's continuously sp2 hybridized. And the delocalization happens to the p orbitals that are associated with each of the carbons in that double bonded system. So for cyclohexane, what we find, or hexene, what we find, for the hydrogenation to cyclohexane, we get about 28 kcals per mole of energy out. Our prediction would be that if you had two double bonds, and I'm going to do isolated double bonds because that's typically what's measured, not the conjugated. The isolated double bonds look like that. And then if you have three double bonds, that would be benzene. So I'd add 28.6 kcals per mole for the addition of H2 from here to here. I would have twice that going from here to here, and I should have 3 times that going from here to here. When you actually do, let me go to the next slide. When you actually do the experiment and you hydrogenate benzene, which is actually quite difficult to do, what you find is that its energy is 49.8 kcals to go from here to here, whereas you predict it to be almost twice that number. Okay? So there's about a 36 kcal difference in energy from what's predicted for 3 double bonds than what you have in benzene. In fact, it's lower in energy than 2 isolated double bonds as well. And it would also be lower in energy than 2 conjugated double bonds. So one of the things, when we say a compound is aromatic, now aromatic used to originally come from the idea that compounds like vanillin or let's see, what's the other one? Clove. You know, they had these good smells associated with them. That's where aromatic originally came from. But now the meaning of aromatic is any compound that has unusually high resonance stabilization. So it's much more stabilization than the 3 to 4 kcals you expect. It has roughly 10 times that increased stabilization. Now, just to be clear, when we say it's increased stabilization, it's lower in energy, not higher in energy, right? So the next question to ask is, how do you know when a molecule is aromatic? And these are summarized by Hückel's rules. Now, Hückel didn't have 2 rules, but we often list it as 2 different rules. Hückel just said, this is what it is, that's how you know it's aromatic. What Hückel said was, it's flat, cyclic, okay, and it's continuously double bonded. But we know that as being uninterrupted pi orbitals. And each atom has a p orbital on it in the ring. So it's flat, right? It's in a ring, and every atom on that ring has an available p orbital. The second part, and which is often called Hückel's second criteria, so the first one is the flat cyclic uninterrupted pi orbital. The second part is that it has to have an odd number of electron pairs. So Hückel formed this as the 4n plus 2 rule. So if you put in 0 for n, that means you have 2 electrons in the pi system. If you put in 1 for n, then you had 6. If you had 2 for n, then you would have 10. But we think about this in terms of numbers of electron pairs. So 2 electrons makes 1 pair, 6 electrons makes 3 pairs, and 10 electrons makes 5 pairs. And we'll apply some of these ideas to these molecules that we're looking at here. So we have benzene. We can see how benzene meets this criteria. So for benzene, we know that this atom and this atom are all sp2 hybrids. Now there's a hydrogen here, so don't forget that. And if you have 3 groups, then it's going to be sp2 hybridized. Every single atom is touched by a double bond in the ring, except for the hydrogens. Well, actually they are too, but every single carbon atom is touched by a double bond in the ring, and as a result, each carbon has a p orbital, and there's an uninterrupted pi bond which extends across all the atoms. Okay. Now, how many electrons are in the system? There's 2, there's 2, and there's 2 like that. So there's a total of 6 electrons or 3 electron pairs. Let's take a look at pyridine. Pyridine shown on the right. Again, you look at it with benzene, you'll notice there's one thing that's not drawn here, and that's this pair of electron sizes here. Okay? So, as a general rule, in the delocalized system, only one pair of electrons can contribute to the delocalization of electrons in the ring. What this means is there's a pair of electrons that's been contributed here as part of the pi bond. So this pair can't contribute. The result is that since this external pair isn't contributing, only the electrons in the ring contribute. So this follows the same pattern as benzene. It has 3 electron pairs, it's continuously conjugated. Now take a look at pyrrole. Pyrrole is just shown down on the bottom of the slide here. Now the nitrogen has a lone pair on it. It looks like this. Right? So here's the thing. If one pair of electrons can contribute on an atom for delocalization, and especially for aromaticity, it contributes. In other words, because this pair of electrons can donate like this and form this resonance structure, like this, okay. Because it can do that, one, and two, because that makes it aromatic, then the system, the parole system, will be aromatic. Because these represent two electrons, two electrons. This represents the third pair of electrons to give us an odd number of electron pairs. So sometimes when we talk about compounds that are aromatic, especially for heterocycles, all right, it's important to draw the resonance contributors in order to understand whether or not the pair of electrons contributes and makes it aromatic. And the general rule is if you can draw a resonance structure that contributes one electron pair, not two, one electron pair, then the system is aromatic or can be aromatic. So aromatic resonance structures are going to be important as we discuss mechanisms on benzene. And we discussed some of this before. So what I'd like to do now is just very quickly give a couple of examples of resonance structures in aromatic compounds or ring structures. So I've given actually 3 different aromatic compounds down below. And we'll talk about each one in turn. We have cyclopentadiene that's shown here. And in cyclopentadiene, it has a very low pKa because of the aromaticity of the ring after you pull the hydrogen off. So if you have a base like OH minus even, it will attack the hydrogen, and you can put the pair of electrons onto that carbon. That gives us this structure here. So when you have resonance structures in rings, there's just a couple of things that you have to keep track of. One of them is you should try not to violate the octet rule if you don't have to. Now, if you're already at a situation where the octet rule is violated, like you have 6 electrons, for example, not more than 8, but you have 6 electrons, and you can move pi bonds, and you just keep moving that octet rule violation around, it turns out that's okay, because it's already unstable as usually a carbocation, and so it's okay to move that charge around. Now, when you have an anion like this one, that's shown here, the way that we push the electrons is called the allylic lone pair pattern. And what you do is you take the pair of electrons that are allylic, which means, right, they're next to sp2 hybridized or double bonded carbon, then you can push the electrons towards that pi bond. In this case, I could have gone in either direction. I could have gone to the left like I did, but you could have also have moved it to the right over here. But when you do that, remember there's a hydrogen here. And by doing that, you could end up violating the octet rule. And so to avoid that, what you do is you move the pair off the pi bond and you place them on the carbon at the other end of the double bond. And so what you end up with is this structure. Notice the arrow is going that way. You'll get this structure that has the negative charge over here now. And that pair of electrons can be pushed, and then you'll go in this direction. And you can keep doing that. You can go all the way around. And what you find out is that pair of electrons in this aromatic system goes continuously around the entire ring. Cycloheptatrienyl cation also has a different pattern. It's just the pi bond movement. You'll notice that this is an sp2 hybridized carbon. So it already only has 6 electrons. So this is electron deficient. And it has 3 groups on it. And so you can just move the pi bond like that. The next resonance structure will be something like this. And all I've done is move the pi bond. And then, you notice this carbon here also is electron deficient as well. But as long as you're not creating deficiencies, normally it's okay just to move them. Creating new deficiencies, it's okay to move those around. Now in furan, what happens is you can take that pair of electrons and you can move it in like this. And again, this is that allylic lone pair pattern that you'll see. And it'll be very much like cyclopentadienyl anion. That's what this guy is. Cyclopentadienyl anion. Or actually, this guy is. It'll be very much like the same pattern. You'll push the electrons all the way around. The other thing that you have to keep track of that you usually try to avoid is you usually try to avoid a positive charge on a more electronegative atom. That's actually what you'll end up with furan down here. It's not that you can't do it, but the most stable structure will be the structure where the oxygen is neutral or has a negative charge usually. In this case, it ends up with a positive charge. So the structure we're looking at, just the structure of furan, this is probably the most stable resonance contributor. A couple of other, oh yeah, I forgot, I put cycloheptatrienol on this one. This is to show you that, in bigger scale that you can move it. And then I'll go ahead and I'll draw a couple of these out. So now we're here, and then this one will move. And these are resonance structures, so you'll end up with this. Sorry, that's kind of a helter-skelter pattern I've got here, because I'm not used to drawing this kind of structure. All right, there you go. Now, an unusual compound is the one that's shown on the bottom left. It turns out even though this is a nonpolar molecule, that it looks like it's nonpolar, it actually has a significantly large dipole with the positive charge, the dipole pointing in this direction. It turns out this is one of the homework problems from, or similar to a homework problem that was given last semester out of chapter 8. What ends up happening with this structure is that this pair of electrons actually goes like that. And this is not something you normally do. But what you end up with is this. You notice that the cyclopentadienyl side looks much nicer than the other side. You end up with that. And you'll notice that each part, this part of the molecule is aromatic, as well as this part. Because of the aromaticity being induced by the separation of charge, what we find is that that charge does separate some, and you end up with two aromatic systems bonded together. There's another way to determine whether or not molecules will be aromatic, and that's by using something called a frost circle. Now, we haven't spent too much time talking about molecular orbital systems, conjugated ring systems, but it turns out a simple way to determine the relative energies of the molecular orbitals is by drawing the shape of the ring structure with the point going down, so that's here, the point going down. And then when you draw the uniform geometric shape like it's shown here, so this is an actual drawn hexagon, what you find is that the relative energies of the molecular orbitals are at the vertices where the lines meet. And so this is what the molecular orbital of a system would look like for 6 p orbitals in a ring. So that includes benzene. What's actually shown here is benzene. When you take the electrons from benzene and you place them in the lower energies, these are all the bonding molecular orbitals below this line. What we find for aromatic compounds is that all the electrons of the system are in the bonding molecular orbitals. Now, if you take a system like the cyclopentadienyl anion, now that's this one here, just to be clear. Again, cyclopentadienyl looks like this. It has 3 pairs of electrons in it. The lower, if you take the center point, that's what we're doing here, take the center point, draw a line, or you take the center point of the pentagon and you draw a line. Everything below that line is a bonding molecular orbital. So what you find is that again, just like in or in benzene, you find for the cyclopentadienyl anion, we find that the electrons are all in the bonding molecular orbitals. Now let's do cyclopentadiene, dienyl cation. That's supposed to be YL cation. That would be this guy. So again, it meets Hückel's criteria, at least in the first part. It's continuously conjugated and flat, but now there's only 4. And what you end up with is these electrons, orbitals, these bonding molecular orbitals are not filled. If you take cyclobutadiene, that's this. That's 4 electrons, so there's 1, that's D here. You have 1, all right, 1, 2, 3, 4. Again, you find that not all the orbitals are filled. And so it turns out there's an interesting thing that happens when the bonding molecular orbitals are not filled, or you have these unpaired electrons. These are essentially radical electrons in the non-bonding orbitals. These compounds are said to be anti-aromatic. Well, these compounds are exceptionally unstable. So essentially, cyclobutadiene behaves like a molecule with 2 radicals in its system, and so does the cyclopentadienyl cation as well. So for a molecule to be anti-aromatic, it basically satisfies the first criteria. That's uninterrupted pi system, so that's flat, continuously conjugated, but it has an even number of electrons in it. And so it turns out that the anti-aromatic compounds are much less stable than even normal non-aromatic compounds. So for example, if I have this, and this, and this on a relative scale in terms of resonance destabilization, right? This is the least stable, and this is the most stable, or has the most stabilization and the least stabilization. In fact, least stabilization is not quite the right term, because these are relatively more unstable. So here are some examples of different aromatic compounds and their electrostatic potential maps. So benzene, I don't have drawn on the left here, but I have thiophene, imidazole, pyridine, and pyrrole drawn. Now you'll notice in pyridine that there's a bright red in the electrostatic potential map. There's a fairly bright red region at the bottom. Right. And then in pyrrole, it's a relatively light blue, which means positive charge. So in fact, pyrrole has a relatively large dipole moment that points in this direction. So what's odd about that? I mean, considering that nitrogen is more electronegative than carbon, you'd expect the negative end of the dipole to be towards the bottom. But in fact, for pyrrole, when you think about its resonance contributors towards its aromatic structure, what you'll find is that when you do the double bond to the nitrogen and you have this hydrogen, it has a positive charge, like this. And again, there's several resonance structures, 5 of them that you can draw for pyrrole as an aromatic compound. And in each one of those structures, there's a positive charge on the nitrogen, or on the hydrogen end. That's actually the hydrogen that I drew it over, but on the hydrogen end of the molecule, because of the delocalization of the negative charge into the ring. So the pair of electrons on the nitrogen donate into the ring and create relatively high electron density in the ring. Now, pyridine is not the same way, and the reason pyridine is not the same way, we mentioned this earlier, is only one pair of electrons can be contributed from the nitrogen to the delocalization. So this pair of electrons for the pi bond, in essence, is a bond from the nitrogen, and then this pair of electrons can't contribute. For thiophene, you'd expect very much the same kind of behavior as you have for pyrrole, that this pair of electrons contributes towards the ring. It's not as great as in pyrrole because thiophene, the molecular orbital size of the sulfur doesn't match very well with the carbon, and so there's a little bit less actual delocalization into the ring. Imidazole is interesting because you'll notice there's a pair of electrons here, and there's a pair of electrons here. Take a moment, and if you want to, pause the videos and try to determine which one of those two is actually delocalized into the ring. So hopefully you came up with that idea, is that pair of electrons delocalized into the ring, and then that leads to a resonance structure with two lone pairs on the nitrogen. And again, talking about the lone pair, this one is in the plane of the molecule. Because remember, imidazole, pyridine, pyrrole, thiophene being aromatic compounds, the molecules are flat, and so we can define a plane, and that pair of electrons is in the plane of the molecule. So to summarize aromaticity from chapter 8, aromaticity gives us increased stabilization. We call that resonance stabilization, and they're much more stable than predicted based on the number of bonds or just delocalization, conjugation that we see in non-cyclic systems. There are two major criteria for determining whether a compound is aromatic. One is that it has to be continuously conjugated and flat. So when we're talking about that, one of the common examples that comes up is we come up with this molecule, for example. I can't draw it right. Let me redraw it in the old-fashioned way. And we talk about whether or not this compound is aromatic, anti-aromatic, or just not aromatic. And it turns out, if you count up, it's continuously conjugated. It has 4 pairs of electrons, and so you would predict that it's anti-aromatic. But in fact, what the molecule does is it bends in order to avoid that, because the anti-aromaticity makes it so much more, less, I should say not more stable, more unstable, but less stable, that the molecule will actually bend to break delocalization. So it actually doesn't meet this first criterion. So it's not really anti-aromatic. The other thing to talk about then is the frost circle. Another way to determine whether or not something is aromatic is draw its shape with the point down. For benzene, that would be like this, and then look to see whether or not the electrons in the system are filling the bonding molecular orbitals. The last thing is when we talk about heterocycles. In heterocycles, you can only use one pair of electrons on any given atom, and so nitrogen is the one that gives us the most difficulty looking at. Typically, it'll be either double bonded or not double bonded, and when it's double bonded to a carbon, the lone pair can't be contributing towards aromaticity, and when it's not double bonded, that is single bonded or in the allylic position, that's like this, for example. This is the allylic position. Then it can contribute, and so that adds to the number of electrons in the aromatic system, or in the ring system. So I had a different title for this slide, and you know from our previous discussions, I'm not a big fan of nomenclature, but it is a necessary thing that we have to do. And so I changed the title of this slide to Nomenclature of Monosubstituted Benzenes is Confusing. Okay, so what do I mean by that? Most of these compounds have names which are based as benzene as the parent, and that is the systematic name. So, for example, toluene is actually methylbenzene. That's its systematic name. Aniline is benzene. I'm not going to write them all here, they don't fit. But you can actually look up phenol, for example, and look to see what its systematic name is. It'll tell you, say, so type in phenol and systematic name. Now, I'll tell you why I'm not going to write all these down, because I actually don't care if you do that or not. So benzene, right? And then to make it into an amine, it'd be benzene amine, like that. This would be benzene carbaaldehyde. So again, this is benzene carbonitrile, I believe, something like that. But reality is almost everybody will use and treat the substituted names. So this toluene, phenol, aniline, they'll treat those as the systematic name. So those are the names that I want you to use when naming these kinds of compounds. I just want you to be aware that there's these systematic names that are out there that most people don't use, okay? Now, benzyl or phenyl, this is what we call these things, aromatic rings, especially benzene rings, I should say, when there's substituents on a larger structure. Okay, now, what do you need to remember? I generally want you to be able, if I said methylbenzene, I would expect you to draw it and be able to name it also as toluene. If I gave you benzene amine, I'd expect you to know the name aniline and be able to draw it. Okay, so I don't care that you memorize the systematic names for these, as this is unusual for nomenclature in organic chemistry, I know. But I want you to be able to take toluene, if I say 3-hydroxytoluene, or if I say 3-methylphenol, I want you to know what that means and be able to draw it. Any name that you give me, pretty much, if it's the systematic name or if it's the substituted name with the it's really a common name of the ring, of the, like the aniline is like, if you give me those names, those are fine as well. But I do expect you to memorize those. Now, how does benzene react? This is a topic that, again, covered in chapter 8. It begins with the reaction with an electrophile. And the characteristics of the electrophile is that it really just needs to be a very strong electrophile. And the reason it needs to be a really strong electrophile is because benzene is exceptionally stable. When the electrophile is attacked by the ring, or reacts with the ring, it can form, it does, it forms a carbocation. And that carbocation is stabilized by delocalization like this, okay? And you're expected to be able to draw all the resonance structures from that delocalization. So for this particular intermediate, that delocalization would result in these resonance structures. And then you end up with this. Something like that. So those are the resonance structures that you can have on this particular intermediate. So the three structures are the resonance contributors for the resonance hybrid. Okay, so now two things can happen following that. One is you can have a base / nucleophile. So this is Z is either a base or a nucleophile depending on how it behaves. A nucleophile attacks like the carbocation, right? And this gives us the addition product. The base is actually a nucleophile for hydrogen, so it attacks the hydrogen. Now, if you do the addition product, this is what you will end up with. If you do the substitution product, this is what you expect. That is, the electrophile substitutes for the hydrogen that was on the ring. in practice, what we find is there is no addition product, and all the product that forms is the substitution product. The reason for this has to do with the stability of the substitution product. Now, the rate determining step is this first step to form the carbocation, which is stabilized, again, this is stabilized by those the two other resonance structures. And then what happens is in the next step, you can either form the addition product or the substitution product. But the substitution product is aromatic. And the addition product is not aromatic or non-aromatic. Because the aromatic product is so much more stable than the addition product, the substitution product is so much more stable than the addition product, none of the addition product really forms. It all goes directly to the substitution product. Now, there are a few common mechanisms that I expect you to know, and the common mechanisms are really the mechanisms for the formation of the electrophile. There are some basic reactions that you'll need to know and have memorized. There's the halogenation reaction, nitration reaction, sulfonation, Friedel Crafts acylation, and Friedel Crafts alkylation reactions. And for each one of those, I expect that you'll be able to draw the mechanism for the formation of the electrophile, as well as draw the mechanism for the formation of the substitution product of benzene. In addition, I expect you to also be able to use resonance structures and be able to explain the stability and why each step happens the way it happens, like we just did for this, all right? So here are a couple of examples of halogenation reactions on benzene using chlorine and ferric chloride, that's iron 3 chloride, and bromine and ferric bromide. So these are essentially chlorination and bromination reactions. The way the electrophile is formed is that the iron forms a fairly strong complex with chlorine, and so the pair of electrons from the chlorine bonds to the iron and creates this complex that's shown here on the right. Now, that particular complex, what it does is by making this positive charge appear on the chlorine, essentially makes this chlorine much more electrophilic because this pair of electrons is drawn towards the chlorine. The result is a strong electrophile in the chlorine. So in the mechanism, we have, I'll do it with the bromine, Br like this, and then the FeBr3, and this is minus and this is plus. This pair of electrons comes out and attacks the bromine. This bond breaks. I'm going to draw it out over here. You form, I'll draw it on this side since I've drawn it on this side, the Br here, plus the FeBr4 complex ion, like that. The positive charge is on the other end of the, and I'll do this, I'll draw these hydrogens in here. The positive charge is over here. This is stabilized by resonance, but then this can come back through and pick that pair of electrons off and close the aromatic ring back up, like this. And the chlorine mechanism essentially follows the exact same pattern. Now, I should point out that how the electrophile gets formed is actually a little bit different for iodine. It turns out in iodine, you need an oxidizing agent. It's often something like H2O2. And that forms the I+, so I guess that would be the ionium ion. And the I+ acts as the electrophile in the reaction. I'm not going to draw all the steps out because it does get pretty tedious to do these over and over again. It does that. and then you end up with there's a hydrogen here, so don't forget that. There's already a hydrogen here. Another I minus, but most likely remnants of the oxidation product of base. Come in and attack that, and then this closes back up, and then you get the iodated, not like the chlorinated or the brominated, so the iodated product. All right. Now, for ferric chloride and ferric bromide, it turns out they're pretty hygroscopic, and so so when they come in contact with water, it deactivates them. So the way it's usually generated is using iron solids, this iron metal shavings, and then you add bromine to it, or chlorine to it, and that forms the FeBr3 ionic compound, and that's actually then creates the electrophile with the bromine. So we say, if you'll notice what it said back here, it says that it's generated in situ. That just means we create the reagent in solution because it's a lot cleaner that way. You don't have to worry about deactivation from water. Of course, you always have to worry about water being in the system and keeping everything dry, but you don't have to worry about the reagent itself being bad because you generate it in solution. So you can find summaries of all these reactions at the end of the chapter. Nitration is another reaction, and this is one in particular that's good to memorize because there's a number of mechanisms that sort of follow this route. The electrophile is this nitronium ion that's drawn at the bottom of the slide for the nitration reaction. Now, the way it's formed is by mixing sulfuric acid with nitric acid. So when you see this on a reaction arrow for the nitration, what you'll see is you'll see something like this, HNO3 and H2SO4. The H2SO4 will actually protonate the nitric acid because it's a much stronger acid than nitric acid, and as a result, this part of the molecule will break off and give us water. And the part that is used in the reaction, this is the nitronium ion, which is the electrophile for the reaction. Sulfonation takes place in a similar fashion. That is, the electrophile that's generated is either this or this, it turns out. It could be either one. It turns out sulfur trioxide, though, follows that same pattern. Hot concentrated sulfuric acid literally means you take sulfuric acid and you literally boil it. You heat it up until it starts to fume. So it's often known as fuming sulfuric acid. And the fuming is actually the sulfur trioxide, I think it's as it leaves the solution. So that is the electrophile. In the mechanism, it's easier to show this in the mechanism. So when you have benzene, I draw bonds in if we do a mechanism. And you have SO3H is what you have. This has the positive charge on it. This bond can just attach like that, and then that would add to one end or the other of that particular double bond. The interesting thing about sulfonation is that the mechanism is reversible. So not only can you add this SO3H group to the ring, but you can also remove it from the ring. And basically the way you do it, it's acid catalyzed. Basically the way you do it is you, in the forward direction, it's fuming sulfuric acid, so H2SO4, and then heat. In the reverse direction, it's dilute acid. So that's for going in this direction and heat. That's just to activate. So you can go from the reactants, like here, to the products, or you can go from the products to the reactants, and they both involve the same intermediate compound in the middle. This turns out to be important later in the chapter when we start talking about ways to control where substituents end up on the ring. And you can block a position on the ring by adding a sulfonate group to it and then removing it later so that that position is available or unoccupied. Okay, so it's one of the uses of that. Now, the Friedel Crafts acylation reaction is one of the more important reactions that we study, and it's actually how we put acyl and alkyl groups on most aromatic rings. So in the acylation reaction, we use aluminum chloride, and we'll go over the mechanism for that in the next couple of slides. But the general scheme is you take an acyl chloride or an anhydride, and then you use aluminum chloride and H2O is this following step. So the first step is the aluminum chloride, and it forms an acyl group. The acyl group is this group with a carbon with a double bond to an oxygen and an alkyl group on the other side. Same thing happens when you use an anhydride, and you'll form an acyl, you'll attach an acyl group. Typically a symmetric anhydride is used. So as far as mechanism goes, I don't know if you've noticed what's happened so far. For NO2, the nitronium ion, we started with nitric acid. I'll put the H on this one like that. And the nitric acid was protonated, and then a group broke off like that. And then in the sulfonation reaction, so again, going back, right, the nitration reaction, this was the nitration reaction. I protonated that, and then it broke off. Sulfonation, I did the same thing. So in sulfonation, I went like this. And this broke off like that. So forming an electrophile by breaking a group off, making an electron deficient in essence, and then putting a positive charge on that atom makes it a strong electrophile. The formation of the electrophile in the acylation reaction very much follows the same pattern. So what I wanted you to see is how we're usually modifying what will become the electrophile so that it creates a situation where it's electron deficient and then much more strongly reactive. So here's the mechanism for an acyl chloride, and it turns out that the aluminum chloride is what we call a Lewis acid. We've discussed Lewis acids before, but it's electron deficient. Aluminum only has the 3 valence electrons when it's bond, so it has this open orbital. So what ends up happening is the chlorine, just like it does in the reaction with the ferric chloride, it becomes this. And if you remember back in Chem 1B, we talked about electrophiles. We talked about complex ions, and we talked about their stability. That's one of the things that makes the aluminum so electrophilic, is that complex ion has a very high formation constant. It makes it really stable. So when we did this reaction with chlorine, if you'll remember, like Cl2, and you had Fe over here, there was a positive charge here that made this carbon much more electrophilic, that is much more able to accept a pair of electrons. But in this case, let me go ahead and erase that because I was going to use that space. For the electrophile and the acylation reaction, what ends up happening is it does this. So what I get out of that is this as my electrophile. And it has a funny name, actually. It's a triple bonded oxygen with a positive charge on it. And that positive charge makes this carbon really electrophilic, and it's called an acylium ion. Sounds like it's a silly ion, right? So, and then it forms the complex ion AlCl4 minus. Okay, this can actually stabilize this positive charge, but we usually don't drop it in there. So the acylium ion is my, I might have two L's in it actually. The acylium ion is the electrophile for this reaction. So it goes like this. I have an R group. And you notice I'm drawing it linearly because this carbon now is sp hybridized, so it's flat. Remove some of the steric strain requirements that we usually find in a lot of compounds. So now we can react this with benzene. And this reaction can go like this. And that forms the carbocation in the ring, and then the proton gets eliminated, and then you end up with your acyl substituted benzene ring. So that's essentially what's happening in the background. Now, I'm not going to draw, like, I'm not drawing the entire mechanism. That is, I'm not drawing like what's going on when the ring closes, but that process is very much the same. The last thing we usually have to do is we add water to it or hydrochloric acid to it, because it turns out this aluminum chloride typically bonds very strongly to the oxygen, so you have to kind of like dissociate it from the product, and so we end up adding water or hydrochloric acid to remove it. The last thing to talk about is the alkylation reaction, and then I'll end this sort of first introduction lecture to aromatic ring structures, and then we'll go on to the second part where we talk about like what we can do with those aromatic ring structures. So the next thing to talk about is the Friedel Crafts alkylation reaction. And in the alkylation reaction, you have to be careful because what reacts with the benzene ring, for the most part, appears to be a carbocation. So what do you remember from like SN1 or E1 mechanisms when you have a carbocation that forms? The carbocation is subject to a couple of things that you usually look for, like elimination and the other one, and the big one is rearrangement. So, for example, if I gave you this as the alkyl halide, give you that as your alkyl halide, draw it a little bit better. So, like propyl chloride, and I did the alkylation reaction, I wouldn't expect to find this is my product because of the potential for rearrangement. Because when it reacts, it behaves for the most part like a carbocation. So I won't get into all the details of like how it happens, but let's just assume that it reacts like a carbocation. So the mechanism, though, barring the discussion of the rearrangement of the electrophile, looks very much like all the other mechanisms. I have an R group, which is my electrophile, alkyl group. It is attacked by the ring to form a carbocation, and a base comes in, and we end up with the alkyl substituted product. Now, here's an example of the kinds of problems that you can have. So this is 1-chlorobutane, and when you react it with benzene using aluminum chloride, what you end up with is, rather than having the primary substituted product, you end up with a secondary alkyl group substituted product as the major product. And the reason is during the reaction, this carbocation which forms, I'll put it in quotation marks, that's what I did up here, that carbocation will rearrange as this, and will lead to a rearrangement which causes a 1,2 hydride shift, causes the secondary carbocation. So if you're doing a reaction where you want that to be your product, then the easiest thing to do really is to start with this as your reactant and end up with a higher percentage of secondary substituted alkyl benzene. Now, one of the other things that is generally wrong with this reaction, and we'll talk about this more in the next section, is that once you put an alkyl group onto a benzene ring, like this, these are electron donating groups. Okay, so because they're electron donating groups, what happens is when the next if you bring another electrophile to the benzene ring, it reacts more quickly. So here's the thing, and the relative positions it says in the 2 and 4 positions. We'll talk about that later. But the first alkylation is actually the slowest alkylation, and then the second and the third alkylations are the fastest. And so often what ends up happening is you end up getting polyalkylation, as you get lots of alkyl groups added to your ring, as many as 3. So in order to run these reactions efficiently, that is, get a high percentage of a benzene ring with a single alkyl group on it, typically they run in a situation where the alkyl group that's being added is the limiting reactant, so the probability of it running into a benzene ring with more than one or with an alkyl group already on it is much lower. So the large excess of benzene that's used in the reaction to avoid double addition products also has to be removed at the end so that you don't have all that solvent in the reaction. It's just to isolate your product. There are several other rearrangements examples. So you'll notice that if you use 1-chloro-2,2-dimethylpropane, right? So this is also known as T-pentyl chloride, because it's 5 carbons. When it reacts in aluminum chloride, you don't get any of the primary substituted, but what you end up with is a rearrangement where you end up getting a shift, okay, from a methyl group to the primary carbon to form this carbocation, and this is the carbocation that adds to the ring. So for alkylation reactions, a simple summary of the reaction is that the mechanism is very similar to the Friedel Crafts acylation reaction, but you tend to get rearrangement, and so straight chain alkylation is not favorable. So this is the reaction from earlier. You get a branched substituent rather than the straight chain substituent. And the other sort of limitation of the Friedel Crafts alkylation reaction is that you tend to get polyalkylation, and so you have to run with a large amount of benzene as excess, and you end up having to sort of purify that in order to get your product out. Okay, so what if you wanted to make this as your product with a straight chain on it? It turns out the best method for doing this to avoid having to use a large amount of benzene in the reaction and also to avoid rearrangements is simply to do the acylation reaction rather than the alkylation reaction. So what you end up doing is you end up doing the acylation reaction, adding this acyl group, and then you do a reduction reaction. And I'm going to show you a couple of different examples of that. But there are a number of ways in which we can handle that and reduce it down to an alkyl substituent. The sort of standard methods are a Clemmensen reduction. So the Clemmensen reduction, you don't need to know the mechanism for that, but it involves zinc mercury amalgam, hydrochloric acid, and heat. And so this is an acidic method, and you end up getting this as your product. The other one is a Wolff-Kishner reduction, and I think we talked about this briefly, but the intermediate for that particular reaction is to go through an imine. So in essence, you go to something like this. And then you can continue to, well, let me draw a part. I'll draw a little bit more of the mechanism so it's clear. You can use a base like hydroxide and then heat, and what it does is it pulls this off like that and then puts the negative charge there, and that picks up a proton from the solvent. Eventually what ends up happening in the Wolff-Kishner reduction, and I do expect you to kind of figure out the mechanism to do it, is you end up getting N2 that comes off of this. We talked about these kinds of reactions where you form a gas and you can favorably form the product simply by allowing the gas to leave the solution. The other reduction reaction uses a similar kind of chemistry, at least in terms of carbonyl groups, and that's called the Mozingo reduction. And that's the formation of a thioacetal. And so in the thioacetal, what happens is you form an intermediate after the first step that looks like this. And so those structures, if you remember from the previous chapter, like 2 chapters ago, you can use rainy nickel and you can reduce that off to get to the alkyl or alkane. And so those are 3 options. One is strongly acidic, one is basic, and the other one is roughly neutral when you do it. Okay, so those are 3 options that people would typically use for reducing off that carbonyl group in the after the acylation reaction. So that kind of does it for this first installment of the online lecture, and then in the next section I'll talk about how a couple more functional group conversions that you can do on benzene rings, primarily oxidation of alkyl groups on the benzene ring. Then we'll also talk about what do you do with substituted benzene rings, what kind of reactions can you do, and we'll talk about what are called activating, deactivating substituents and orthopair directing substituents, and then also the effects of having other atoms other than carbon in the ring, so we call those heterocycles.